Welcome back to the second half of our video on topic 6.9, which is substitution using, or integration using substitution. In this video, we're going to take a look at a couple of things that we just didn't get to in our last video using substitution. Starting with example 7, the change of variable method. So here's a slightly different type of integration using substitution problem. An integral of x times root 2x minus 1. The reason why this is different, if we substitute for 2x minus 1 like we normally would, the derivative of that is 2. But we have this x out in front, and we're not going to be able to get rid of it. So there's some extra work that needs to be done to do this one. Let's take a look at how this works. So yeah, we cannot directly integrate this, so we're going to have to substitute. And yes, you're still going to want to substitute for what's inside another function, so in this case 2x minus 1. However, when we take our derivative here, we get 2 dx, and then we get 1/2 du equals dx. All right, so this is going to allow us to get rid of the 2x minus 1, that'll be u, and we get rid of dx, it'll be 1/2 du. The problem is this x right here. All right, what we need to do then is take our original substitution and solve that for x by adding 1 and then dividing by 2. And now we can substitute u plus 1 over 2 in for x. Let's see how this looks in our integral here. So integral, instead of writing x, we're going to write u plus 1 over 2. Instead of writing root 2x minus 1, we're going to write root u. And instead of writing dx, we're going to write 1/2 du, or du here, and 1/2 out in front. Okay, so simplifying this a little bit, I could take this 1/2 and pull it out in front as well. So now it becomes 1/4 integral u plus u times u to the 1/2, u plus 1 times u to the 1/2 du. Still can't integrate this yet, but now with one more small step, this becomes a very simple function to find the integral of. So now I get 1/4 times u to the 5/2 over 5/2 plus u to the 3/2 over 3/2 plus c. And doing a little simplifying there, so 1/4 times 2/5 u to the 5/2 plus 2/3 u to the 3/2 plus c. All right, and a little bit more substitution, and then some back substitution will get us 1/4 times 2/5 will be 1/10. And then resubstituting for u, we would get 2x minus 1 to the 5/2. 1/4 times 2/3, that would be 1/6. 2x minus 1 to the 3/2 plus c. All right, let's try another example here. If you want to try this on your own, you're welcome to pause the video at this point and give it a shot. Otherwise, let's take a look at, let me turn my do not disturb on here, at this next problem. So we're going to want to substitute for x plus 4 because that's not only in the denominator, but it's also inside of a root. So that tells us we want to substitute for that. The derivative of that would just be 1, so du equals dx. All right, that will allow us to get rid of the x plus 4 and the dx, but we still have that 2x plus 1 up top, which we're not going to be able to do anything with. So let's subtract 4 from both sides, and we get u minus 4 equals x. So now I can get rid of all of the x's. And there we have it. Okay, now with a little algebraic manipulation, we end up with 2u minus 7 over root u du. We could split that now into 2u over u to the 1/2 minus 7 over u to the 1/2. And simplifying that will give us 2u to the 1/2 minus 7u to the negative 1/2 du. And at this point, finally, we can take our antiderivative. So it would be 2u to the 3/2 over 3/2 minus 7u to the 1/2 over 1/2 plus c. All right, resubstituting back in and doing a little simplifying, we would get 4/3 x plus 4 to the 3/2 minus 14 x plus 4 to the 1/2 plus c. All right, what about definite integrals? We can do substitution on definite integrals as well. So let's take a look at the first one here. You're going to want to substitute for that inside function. So let u equal x squared plus 1. So then du equals 2x dx. Now notice we only have a 1x dx there, so let's get rid of that 1/2 by dividing. And now my integral becomes 1/2 integral. Don't worry about the bounds yet. We'll get there in a second. X dx becomes du, well, 1/2 du, and we're left with u cubed du. All right, there's a reason why I did not put the bounds there. You cannot write 0 and 1 on the bounds. Those are x bounds, and there are no more x's left in our equation, our integral here, right? So we need to get those x bounds and change them to u bounds. How do we do that? Simple. We need an equation that relates x and u together. And there it is. Put 0 in for x, and you get 1 back. So our lower bound is now 1. Put 1 in for x, and we get 2 back. Our upper bound is now 2. And now we can go at this problem like normal. So u to the 4th over 4. No plus c, because it's a definite integral. So 1/2 times 2 to the 4th, which would be 16 over 4, which is 4, minus 1/2 times 1/4. And that would give you 2 minus 1/8, or 15/8. Now, if you read the directions at the beginning, there are 2 ways to do this. This is the better way to do it. The other way to do it would be after doing this, to back substitute back in the x squared plus 1 and then use the original x bounds. That is not the better way to do it. Okay, this is a much quicker, easier way to do it. All right, 8b. Clearly, we're going to want to substitute for the 2x minus 1, giving us du equals 2 dx. There's no 2 in the problem, so let's get rid of that 2. So 1/2 du equals dx. But we also have this silly x here. So we got to do what we did in the last slide and solve this for x. So now my new integral becomes 1/2 integral. We got to change the bounds as well. We'll do that in a second. U plus 1 over 2 over root u du. Changing the bounds, if we put 1 into here, we get 2 minus 1, which is still 1. If we put 5 into here, we get 10 minus 1, which is 9. All right, and now we have our new integral. So let's do some simplifying here. We get 1/2 from 1 to 9 of u plus 1 over 2 root u. Actually, I'm going to change that to 2u to the 1/2 du. And if we split this, which is going to make this much easier to do, so it would be, actually, I'm going to also take this 2 out in front to make this 1/4. So u over u to the 1/2 would be u to the 1/2, and then 1 over u to the 1/2 would be u to the negative 1/2. du. So that's 1/4 u to the 3/2 over 3/2, which is 2/3 u to the 3/2, plus u to the 1/2 over 1/2, which is 2 u to the 1/2. From 1 to 9. All right, I'm going to multiply that 4 in first, make it a little easier on myself in the end here. So this would be 1/6 u to the 3/2 plus 1/2 root u from 1 to 9. All right, let's do some algebra. If you put 9 into there, you would get 1/6. 9 to the 3/2 would be 27, plus 1/2 root 9, which is 3, minus 1/6 plus 1/2. After a lot of algebraic manipulation, you should end up with 16 over 3 as your answer. All right, so like I said earlier, once again, we have two options here. You can do it the way I did it, which is definitely the much better, easier way in my opinion. Or you could back substitute and go back to the x's. But that's just doing extra work in my opinion. So this is the way I would highly recommend you doing. All right, example 9. If the substitution u equals x over 2 is made, what does this new integral become? All right, let's do this. U equals x over 2, which means du equals 1/2 dx, or 2 du equals dx. That would get rid of the dx and the x over 2, but we still have this pesky x in the denominator here, so we're going to have to solve 2u equals x. All right, so now my integral becomes 1 minus u squared over 2u times, oops, sorry about that, times 2 du. Okay? So what that would end up doing would cancel out those 2's. We're left with 1 minus u squared over u du. Now we got to worry about the bounds. If we put 2 in for x here, we would get 1 back. If we put 4 in for x here, we would get 2 back. So looks like our answer is D. Example 10. The twice differentiable function f and g are defined for all real numbers x. Values of f and g for various values of x are given in the table below. Evaluate. All right, this is not going to be able to do this without substitution, so let's substitute. The inside function there is f. So our derivative would be f prime dx. Hey, look, that's exactly what this question was asking for, f prime dx. So now my new integral becomes, the integral, we're not going to worry about the bounds yet, we'll get there in a second, g prime of u du. The bounds, if you put 0 into here, f of 0 would be 1. If you put 5 into here, f of 5 would be 3, so our new bounds are 1 to 3. Taking the antiderivative of g prime, we get g from 1 to 3. So finally, using the fundamental theorem, we get g of 3 minus g of 1. G of 3 is 3. G of 1 is 10, so 3 minus 10 would be -7. All right. So we should already know these 6 trig integrals, but we're missing 4 of them. We're missing the 4 basic functions, the integral of cosecant, the integral of secant, the integral of tangent, and the integral of cotangent. Okay? You can do all 4 of these by hand, as I'm about to show you. However, it is in your best interest to simply, once you see them, to memorize them. So in example 12a, I am going to go through the proof of the integral of tangent. So the integral of tangent, you can change the sine over cosine, substitute for cosine, and you should get this. Using the logarithmic integral, and then resubstituting back in, you get this. And doing the integral of cotangent can be done the same way. And you can do that every time you see integral of tangent or cotangent. However, it'd be much easier if you simply memorize the integral of tangent. The antiderivative of tangent is negative natural log cosine x, absolute value of cosine x plus c. Same thing over here. We could do this every time for the integral of secant. So you have to multiply by secant plus tangent over secant plus tangent. Who's going to remember to do that? Simplify, substitute for the denominator. We get here, take the antiderivative and resubstitute back in, and there's your answer. Or you can simply memorize. The antiderivative of secant is this. And cosecant can be done in the same manner. So, to summarize all this up, here are your 6 basic trig function integrals. Now, don't forget about these extra 4 right here that we should already know. But the 6 basic ones here, it's in your best interest to simply memorize them. So if they come up, you can do it without doing all that work we just did in the last slide. Okay, speaking of which, let's take an example problem. Evaluate this integral. So 1 plus tangent squared, you should remember that from your pre-calculus days. 1 plus tangent squared is secant squared. There's an identity, a Pythagorean identity, that proves that. The square root of secant squared, well, that's just secant. And if we have memorized the antiderivative of secant, we can jump right to the antiderivative right now, which is natural log absolute value secant x plus tangent x from 0 to pi over 4. And now it's just a matter of knowing your unit circle. So we have natural log secant pi over 4 plus tangent pi over 4 minus natural log secant 0 plus tangent 0. So that's natural log. Secant of pi over 4 is root 2. Tangent of pi over 4 is 1. You don't need the absolute value bars anymore since that's positive. Minus natural log secant of 0. Remember, that's just the reciprocal of cosine of 0. So that's 1. Tangent of 0, sine over cosine, will be root 2. I'm sorry, tangent of 0 is not root 2. Tangent of 0 is 0. Okay, so this is just the natural log of 1, and we know that we should know the natural log of 1 is 0, so technically all this is gone, and our final answer here is natural log of root 2 plus 1. Okay, that is it on topic 6.9, and that's actually going to put a wrap on our 6th unit. I hope you enjoyed today's video, and we'll see you again soon.